Hi and welcome. Electric motors are used everywhere every day. And one version I find very interesting is the so-called BLDC brushless LRK Outrunner type. An electric motor converts electrical energy to mechanical energy. The mechanical rotation can be used to spin fans, propellers, gears, and other type of applications and appliances. A brushless BLDC Outrunner motor spins its outer shell with the permanent magnets around its stator, and that has some benefits. In the beginning of 2000, the so-called brushless motor or BLDC motor was not as common as today, and the so-called Outrunner motor was quite rare, especially if we look at the RC hobby scene. Thanks to the DIY scene or community, the LRK type Outrunners emerged and soon became very popular. The LRK name comes from the designers. Benefits of the Outrunner motor. The Outrunner stator is easier to wind than a traditional inrunner motor. Other advantages is the torque. With its high torque it can produce, makes it possible to operate it direct drive without gearbox. That always comes with an efficiency loss. Some Outrunner myths that often comes up is that it's not as efficient as an inrunner motor, that it gets hot and can't dissipate heat as good, or that it's not suitable for high RPM applications. It's just as good or better in all of the above. Here are some disadvantages of the Outrunner. It's more demanding for the ESC, electronic speed controller, and it needs to be set up right. Due to its large diameter, it can be a tight fit in some applications. Let's take a closer look at a BLDC brushless inrunner also. Therefore, it's easier to understand the differences between the types. In the inrunner, the rotor and the magnets are placed inside, and outside the rotor are the stator with its windings. In high RPM use, the rotor and its magnets needs extra support with Kevlar wrapping, so the magnets don't get loose due to the centrifugal forces. If we take a closer look of the different parts of the Outrunner motor, and in this example an LRK type Outrunner, with 12 stator poles and 14 magnets. The rotor and its magnets rotate 7 times slower than the field, and this is one of its secrets to be able to produce high torque. Every second stator tooth is winded, and the 14 magnets are placed with north and south polarity, as seen in the animation. We can take a closer look at the individual parts, and in this case we have a front cover plate in aluminium. The stator tube holds the stator, and inside the ball bearings are located, pressed to fit or glued into place. The stator consists of laminated sheets that are stamped or laser cut. The rotor ring, or can, as it's also called, houses the permanent magnets inside, fixed inside by glue. The stainless steel shaft is fixed by the back plate to the rotor in this example. The stator consists of thin laminated sheets of metal that are electrically isolated to each other. This is to prevent eddy currents. High-quality motors have thin sheets that are laser cut. In this example, the stator have an outside protective coating to insulate the stator from the copper wires. The copper wire are wound around the stator teeth. It's covered in an enamel coating to insulate it. The 3 exiting silicon wires or phases are later attached to the electronic speed controller. The 14 neodymium magnets are glued into place. On premium motors, the rotor are dynamically balanced and the magnets have extra support to better handle vibration and extreme maneuvers depending on use case. Let's take a closer look at this larger Outrunner that is a so-called DLRK type. The 12-tooth stator have 3 phases of windings or groups. Each phase is winded on 4 stator teeth in a DLRK scheme. The stator sheets are stacked and then insulated with protective sheets in this case. We wind the stator with some high-grade copper wire that then goes onto the stator tube. Here we also have extra support for the magnets that are glued into place. If we attach a speed controller that has an electrical source in terms of a battery, the speed controller can apply current to the coils so we get an electromagnet. The interaction between the stator and rotor with its magnets creates the motion of the rotor. When the magnets push and pull the rotor, this creates a rotating motion with a constant torque, and we can, for example, power a propeller. That in turn can power a plane or a drone. And with that said, all I can say now is thank you for watching.